Okay, so here we started this problem by drawing our support reactions at A and D. We took moments about the pin at A to solve for dy, and some forces in the y direction to solve for ay. And some of the forces in the x is 0. There are no applied forces in the x. So ax was equal to 0. So here we had ay was 0.5 kilonewtons. Dy was 1.5 kilonewtons. Okay, and then we started at joint A. We drew the free body diagram here of joint A. And we solved for AB and AE. So we had AB was 0.58 kilonewtons in compression. AE was 0.29 kilonewtons in tension. Okay, let's sketch that on our force summation diagram here. AE was 0.58 kilonewtons compression. AE 0.29 in tension. So that's where we left off last time we met. From there, hopefully you were able to complete this problem for homework, but I want to go ahead and go over it together. It's not a graded assignment, just an opportunity for some extra work and extra practice, really. All right, so we said last time that we met, when we're working the method of joints problems, we just follow the joints in a truss and solve using a free body diagram of each joint until we've completed the truss. And so we could jump around if we want to, or we could go to the next logical joint and kind of work in a more organized pattern here. So here, if I'm going to the next joint, I would choose B or E. If I were to look at E, I've got BE, which is unknown, CE, which is unknown, and DE, which is unknown. So if I want to solve joint B, I've got BE and BC. So there's only two unknown members at B. So B is the next logical place to look. Okay, so we want to draw free body diagram of joint B. Okay, so we've got the joint here. We've got 0.58 kilonewtons in compression. Which we know. Okay, and then BC is acting, we're going to assume it's acting in tension, but BC is a horizontal member. So we'll draw it in tension. BC. And then we have BE, which is also unknown. Okay, BE here. So we'll draw it in tension as well. Okay. Now with our given angles here, we've got 60, 60. So that means that this angle would also be 60 degrees. Okay, and given that this is a symmetrical triangle, you know, this angle 60 degrees, this angle is also 60 degrees. So all these interior angles are 60 degrees. Since we were told that this is a symmetrical truss. Okay, so we can sketch our angles here, 60 degrees, 60 degrees, and we can even reference the x-axis for this angle 60 degrees. Okay, this is one of those cases where it is helpful to name the forces or number the forces so that we can draw our chart. Okay, so I'm going to call this force 1. We'll call BC force 2, and BE will be force 3. Okay, so I'm looking at force number 1. You know, it's going to have an X and a Y component. So we can sketch those here. The Y component would be positive going up. So F1Y would look like this. Fx is to the right. So we've got F1x, which looks like this. Okay, BC is acting entirely in the X direction. And so we have BEX, as we've drawn it, that's to the right. And BEY would be down, so negative BEY. Okay, so we want to create a table here with our forces. Force 1, 2, and 3. The components X and Y for each. Okay, so force 1 here, F1X is equal to F1 cosine 60. So 0.58 kilonewtons cosine 60. That gives us a positive 0.29 kilonewtons for F1X. Okay, I've combined this all in one chart just to kind of show you how that looks. It does look a little bit messy. So if, you know, if this is, you know, it's too much on one sketch here, then, you know, you can always go out to the side and resketch F1 and F3 to show the components. F1Y is going to be 0.58 times sine 60. Okay, that's also positive since it's up. Okay, so that gives us positive 0.502 kilonewtons for Fy. Okay, F2 is acting entirely in the X direction, so F2 has positive BC, the X component, 0 for the Y component. Okay, F3, we've got an X and a Y component, so BEX will be BE cosine 60 since it's adjacent. So BE cosine 60 degrees equals positive 0.5 BE. And then BEY is negative BE times sine 60. Okay, negative, since drawing it in tension makes the Y component go in the downward direction. So that gives us a negative 0.866 BE for Y. Okay, so once we have the chart, we can sum the forces in the X and the Y direction. Okay, again, we can look at our table here and see that in the X we have BC and BE, so there's 2 unknowns in the X, but in the Y just 1. So we can start by summing the forces in the Y direction to solve for BE. So we have 0.502 kilonewtons plus 0 minus 0.866 BE equals 0. So we get BE equals 0.58 kilonewtons. And that's in tension since it's positive. Now we can sum forces in the X equals 0. We have 0.29 kilonewtons positive plus BC plus 0.5 BE equals 0. So just summing everything in our X column here. We've already solved for BE, so we'll substitute in 0.58 kilonewtons for BE. And solving for BC, we get BC is equal to negative 0.58 kilonewtons. Negative means compression. Okay, so any questions about our free body diagram of B? Okay, so we want to go back to our force summation diagram and translate these numbers. So we've got BE is in tension 0.58 kilonewtons. So we'll draw these arrows going away from the joints to show tension, 0.58 kilonewtons. And BC was compression. So those arrows going towards the joints, 0.58 kilonewtons here in compression. Okay, so once we get to this point now, we could go over to joint C. There's 2 unknowns. We could go down to joint E, and there's 2 unknowns. I'm going to go to joint E here, just because this looks symmetrical, okay, but we need to put the numbers to it. So let's go to joint E. Okay, so this is our free body diagram, joint E. Okay, so we have EA, which we've solved for. We know that's in tension. So we'll show this 0.29 kilonewtons, EA. We know that EB is also in tension. So we'll draw that here, 0.58 kilonewtons. Know that the angle between them here is 60 degrees. So then our 2 unknowns are EC and ED, so we'll show both of those in tension. So EC and ED. And we know that these angles are also 60 degrees. Okay. So now we want to sum the forces in either the X or the Y direction. Okay, we could either create a chart. Again, I want to show you all how to do it both ways, with or without the chart. So this time I'm going to just sum the forces in the Y direction first, since I can see that there are 2 unknowns in the X here. So we'll start with summing the forces in the Y. Okay, so in the Y, we have 0.58 kilonewtons times sine of 60. So the y component of that force, 0.58 kilonewtons times sine of 60 degrees. Okay, so that's the y component of this force. And then we've got the y component of EC. Okay, this term is positive. EC is positive the way that it's drawn. So EC times sine 60. Okay, and those are all the only two y components we have. So we'll set that equal to 0. Okay, so solving for EC, we get EC equals negative 0.58 kilonewtons. Okay, negative meaning that EC is in compression. Okay, now if you look at this like initially, you might think, well, EC has to equal this force, right? Since these two are kind of pulling against each other in EC and the 0.58 kilonewtons are opposite here. So they are equal in magnitude, but the thing to remember is the X and the Y forces have to balance. So here the X's are drawn opposite, but the Y's are drawn the same. So both of them are drawn with positive Y's, which is why we end up with a negative for EC here, which is why EC is in compression. Okay, now we'll sum forces in the X. Set that equal to 0. We've got negative 0.29 kilonewtons minus the X component here, okay, which is 0.58 kilonewtons times sine 60, excuse me, cosine 60. We're looking at the X component, cosine 60. Plus, okay, EC cosine 60. Plus ED, all equals 0. Okay, so all four of these forces have an X component. We've got negative 0.29 kilonewtons. The X component here, which is negative 0.58 cosine 60, EC cosine 60, and ED. Substitute in here negative 0.58 kilonewtons for EC. And solving for ED, we get ED is equal to 0.87 kilonewtons in tension. Okay, so looking back at our force summation diagram, it's obvious that the forces are greater here, right? ED has a higher value for force compared to AE, and that makes sense when we look at the applied forces and the support reactions. We've got 0.5 kilonewtons here at A, but at D we've got 1.5 kilonewtons, and we also have this 2 kilonewton force here on the right side of the truss. So it makes sense that those forces are different and slightly greater on the right-hand side of the truss. So ED we said is in tension. So we'll draw these arrows going away from the joints there. 0.87 kilonewtons tension. And EC is in compression. So those arrows will be going toward the joint. 0.58 kilonewtons compression. Any questions on the free body diagram for joint E? All right, the last thing that we need to do is solve for CD. So we could look at joint C, which has 3 applied forces, 1 unknown, or we could look at joint D, which has 2 knowns, 1 unknown. So let's look at joint D here. So for joint D, we have the force we just solved here for ED, tension, 0.87 kilonewtons. We have our support reaction here in the Y, 1.5 kilonewtons. And then DC, which is unknown. So we'll draw that in tension. Okay, so we know that this angle is 60 degrees. All right, looking at this one, we could solve for forces in the X or the Y to get DC since it has both components. I'm just going to hear some of the forces in the Y equal 0. So for DC, we have positive, since Y is up, DC times sine 60. Plus our support reaction of Y plus 1.5 kilonewtons equals 0. Okay, solving for DC, we get DC is negative 1.73 kilonewtons. Negative, again, meaning compression. Right, so we'll show this on the force summation diagram with arrows towards the joints. 1.73 kilonewtons here, compression. And again, just kind of doing a does it make sense check. We've got compression on the top here all the way around. We've got tension on the bottom. Okay, and we've got a mixture of tension and compression internally. So in terms of the signs, at least the signs do make sense. In terms of the forces, again, the forces are slightly greater on the right side of the truss than they are on the left side of the truss, which makes sense due to the fact that we have an applied force on the right side of the truss, making the support reaction greater on the right side of the truss as well.